In this video, we are going to use the law of conservation of momentum to analyze a completely inelastic collision. If you recall what a completely inelastic collision is, it's a collision between two objects where after the collision they couple together and become one and then move with a common velocity. So I'm going to use an example of two trains that are going to collide gently when they couple and then move off together as one. So the two boxes over here, these are going to be the two trains. I'm going to call the first one train 1. Its mass 1 is going to be 3 kilograms. So these are like toy trains, not large ones. This is going to be mass 2. It's going to be 15 kilograms. And initially this first car is going to be traveling at 3 meters per second. So velocity 1 initially, that's the I. And the second is going to be at rest. It's going to be just sitting there, waiting to be coupled. And then they're going to couple after, so a collision occurs, and they're going to move off together as one object with some common final velocity, which I don't know. And I want to find that common velocity. And because there's a little collision here and the mass increases, I would guess that it's a little bit less. So for the momentum model, it's a 5-step process. The first step is to define the positive direction. So I'm going to define the positive direction to be to the right, just like you do in math class. And the reason why we need to do that is because momentum is a vector quantity, has a direction, so we need to decide and determine which is the positive direction. The next step, we make a statement of the conservation of momentum. We actually say Pi equals Pf. Momentum initial equals momentum final. And it's more than just writing it down. It's defining what the initial and final points are. So the initial and final points are, for this particular problem, initially it's when one object is moving and one object's not, so before the collision, and then after the collision when they move off with some common velocity here. That's the final. Step 3, we draw the momentum buckets. So each of these buckets represents an object. This is the momentum bucket for the first object, or the first car. This is the momentum bucket for the second. And this larger one represents the two masses combined. So the question you ask yourself is it moving? Does it have a velocity? So is the first object moving? Absolutely. It has a velocity. In fact, it's 3 meters per second. Therefore, it has momentum. The second object is not moving, so we leave it blank. And the two objects move off with some common velocity here. Right there, like that. So when we fill in the buckets, it aids us in actually writing the equation. So as you can see here, here's a general equation. Because this bucket's empty, this doesn't exist, and we're going to be left with M1 V1 initial actually equals, because this one's 0. Get rid of that right there. M1 plus M2 times the common final velocity. So that's our equation. Simply by filling in the buckets, we can determine which terms exist and which don't. Step 5 is solve. So this is just the math part. So now we need to solve for V final. So M1 V1 initial equals M1 plus M2, because it's the total mass, because remember both objects are coupled together here, times some common final velocity. So if we solve for final velocity, we get M1 V1 initial, and I'm going to divide by M1 plus M2, and if I plug in the numbers here, I get the mass of the first guy is 3, his velocity is 3 meters per second. The mass is 3 plus 15, which gives me a grand total of 9 over 18, which is 0.5 meters per second. And because we come out with a positive quantity as opposed to negative here, box your answer, it is moving to the right, as we stated here. If you get a negative sign here, that implies moving backwards, like maybe a billiard ball hitting another one and one bouncing backwards. So the plus and minus sign makes a difference, and it determines direction, again, as I stated from this reference there. So for momentum type problem, it's a 5-step process. You define a positive direction, which we did here. We make a statement of the conservation momentum, and it's more than just writing it down. It's actually determining what the initial and final points are, in this case before the collision, after the collision, which is typically the case. We fill in the buckets for the appropriate things that have momentum or velocity. We write the equation, and then step 5 is solving with the appropriate numbers. So those are the steps you would follow to solve a momentum type problem with an inelastic collision.